So yeah, my project was looking at using satellite imagery to identify bare soil along with using image classification tools. So the problem is that post-harvest soil disturbance assessments are generally carried out using ground-based methods such as alignment, transects and plots, and these methods are usually labour-intensive and time-consuming. As satellite imagery becomes more readily available with daily updates and high resolution and advancements in imagery classification tools, there's the opportunity to use these to analyse the entire site instead of making a statistical assumption from the plots and transects. So I analysed 7 sites throughout the South Island, 3 of which were in Nelson, Marlborough area and 4 around Christchurch. And at each site, I carried out 30 ground truth points, and these points were split into 2 lines of 15 points, which were spaced at 10-metre intervals. At each point, the location was recorded using the GPS and returned to actually 10 to 15 centimetres for each point. Also carried out a visual inspection at each point to determine the major land cover, whether it be disturbed or not disturbed. And if it was not disturbed, it could either be like slash or vegetation that was left on site. Once I had the ground truth points, I could collect the satellite images of each site, and this was the images were tried to get the images that were taken closest to the day that ground truth was carried out, while also sort of taking into consideration the time of day to minimise the shading effect of the images, and also looking at like cloud cover. The images were taken from a planet scope constellation, and they had a resolution of 3 megapixels. So that's the original image there, and then you can rearrange the spectral bands of the satellite image to create like a near-infrared image and get a bit of contrast between the bare soil and the slash and vegetation. So the dark areas there are the areas of disturbed land or bare soil, while the blue to white areas are the slash and vegetation. And then you can create training samples from this by zooming into areas of like a known class. So you can zoom into this dark spot here and select all the pixels that look like they're bare soil. And this just comes down to the analysis interpretation of the pixels. So you could also get a slash and vegetation training sample up there. And you want your training samples to cover the entire site so you can capture all the variability for each class. And once you have your training samples, you can evaluate them using the tools on ArcGIS. So this is just an example of down here we've got a scatter plot for the training samples where the red shows all the pixels that were classed as bare soil, and the green is the slash vegetation. And you can use both of these to sort of identify how accurate the training samples will be, and you can find areas of overlap, like you have a bit of overlap here between the 2 different classes, and you can go back and redo your training samples until you get a better separation between them. And that just helps improve the accuracy of the classification. So once you have your training set, you can use it to train classifiers, and I use 2 different classification methods. One was the maximum likelihood classification, which is a more traditional method and it's been around for a long time. And the other classification tool I used was the support vector machine, which is a more recent classification method, and through literature it generally outperforms the maximum likelihood, but not always. So there we have a final classified image where the red areas show the disturbed land and the green is the slash vegetation. And you can also see where those 2 black lines on the top right where my ground truth points were carried out. And So you can zoom in onto these points, and you can compare your results from your ground truth data and each pixel that it represents, and use this to fill out a confusion matrix. Just on the next slide, and that'll show you which pixel, how many pixels have agreed with the ground truth data to the classification. So the 5 and the 18 on the diagonal there are the pixels that agreed between the two, and then the other two numbers are the ones that disagree. So then from here, this splits out an overall agreement, and for this example, there's a 77% agreement between the ground truth data and the classified image. And then it also provides a kappa index of agreement at 44% down the bottom, and this is expected to be lower than the overall agreement as it takes into account the agreement due to chance and subtracts that from the overall agreement. Looking at the best case scenarios for across the 7 sites and taking the average when using the support vector machine classifier, it returns an overall agreement of 72% and a kappa of 0.27, and while the maximum likelihood classifier was slightly lower, 68% and 0.23 kappa. You can see from the picture here that it easily picks up large disturbances such as skid sites and roads and larger trails, and this was true for both classification methods. Some limitations of using this tool is that mixed pixels, which are abundant for image classification, is a pixel that contains more than one class. It's not a pure pixel, it has a little bit of disturbed band and a little bit of slash or vegetation, and because the output is a hard classification, it's either is disturbed or it's not. It limits the accuracy of this classification. Then also you have your shaded areas, which have a great impact. As you can see there, that shaded hill slope there is returned instead of all slash or vegetation, but there could be areas of disturbance present, but it changes the reflectance and returns it as being just slash or vegetation. Also, I had only limited ground truth results, as generally carry out a random scatter plot over the entire site, but it just wasn't going to be feasible in the scope of the study to do that for every single site. So I think this will be a useful tool depending on the required accuracy of your disturbance assessment, as it analyses the entire site pixel by pixel. I think there is a opportunity for further assessment using more ground truth data to get a better reading of between the classification methods and provide more accurate results. And there's also high resolution satellite data becoming more available. Like the 3 megapixels, there's are going to be satellites with 50 centimeter resolution coming out soon. There's a summary. I found there's a high overall agreement using both classification methods, but there's only a fair kappa index of agreement, and that fair agreement was taken from a table throughout literature, which there's no universal agreement between these kappa index values, but looking at the majority of those, that they say 0.21 to 0.4 is fair agreement for a kappa value, and both of those classifications fell within that. I confirmed that the support vector machine classifier outperformed the maximum likelihood classifier, and both classifiers identified large disturbances, but they struggled with the smaller disturbances. Thank you.